Ladies and gentlemen, I'm honored to have been invited to speak at this conference. I'm a PhD student from Tianjin University and currently doing some research on intelligent fault diagnosis. Today, my topic is diesel engine fault diagnosis based on deep transfer learning. The content of this presentation is divided into 4 parts. In part 1, I will introduce the two typical intelligent fault diagnosis methods. In part 2, I will give an overall design method based on deep transfer learning. The third part concerns fault dataset introduction and test results. And finally, I will make a conclusion. Before entering the theme, let's look at what is fault diagnosis. Traditionally, fault diagnosis relies on the rich experience of engineers to diagnose engine faults based on abnormal sound or abnormal merit date, which is offline, delayed, and nearby experience-driven. Intelligent fault diagnosis does not utilize engineers' experience or knowledge, but uses machine learning theory to adaptively learn machine fault diagnosis knowledge from collected data, which is online, real-time, remote, and data-driven. We know diesel engine is the main driving force in industry, agriculture, nuclear power, and other fields. The mechanical components of the diesel engine are prone to various faults due to their complex structures and poor working environments. Key to ensure the operation safety is to establish a reliable fault diagnosis system. At present, the widely used intelligent fault diagnosis methods can be divided into two categories: feature-driven machine learning and data-driven deep learning. Feature-driven machine learning is based on signal processing for feature extraction, feature selection, and state recognition, which requires high expert experience, takes a long time to design, and cannot ensure the versatility. And data-driven deep learning trains deep neural network based on sufficient historical fault data and mask the high-dimensional features, which can reduce depends on expert knowledge, shorten model training time, and enhance model generalization abilities. Data-driven intelligent fault diagnosis has attracted extensive interest recently, which is deeply related to big data and deep learning technique. However, in actual engineering scenario, the collected real-time data has two characteristics: imbalance and no label. One of the reasons is that data engine works in a health state for most of the time, and the other is that it's unpractical to interrupt the engine's operation frequently, which causes the fault data stored but the fault type lost. When available fault data is limited, deep learning training is easy to be overfitted and the generalization ability is affected. So what we need to solve is the problem of limited fault data. Therefore, a method based on deep transfer learning is proposed to overcome the problem of limited fault data. The proposed method contains two essential steps. The first is to establish a pre-training model, and the second is a transfer learning solution. Next, these two steps will be discussed in detail. For step 1, inspired by the classic CNN and LSTM, a wide convolutional long-short-time memory neural network is constructed to improve noise immunity. The two advantages are: one, the first convolution layer uses a wide kernel. When the noise is large, choosing a larger kernel is beneficial to improve the anti-noise performance. An LSTM is added after the last pooling layer in the latter part of the network. Consider the order of the features to improve the fault tolerance in harsh noise environments. For step 2, the fault diagnostic process of the model transfer based on WCCL is shown in this figure. At first, to fully pre-train the proposed model based on the constructed large-scale labeled source domain data, the parameter of each layer of the pre-trained model obtain the diagnostic knowledge of the source domain. The second step is to freeze the low-level parameters of the pre-trained network and use a small number of target domain training samples to fine-tune the high-level parameters because the features learned by the deep neural network are more general in the first few layers and more specific in the high level. Finally, with the help of model transfer, diagnostic model suitable for the target domain is established. Well, let's move on to the next point, test results. The test data comes from a 6-cylinder diesel engine, and the main technical parameters are shown in this table. The test simulated the 11 common faults in the fuel system and valve train, as shown in this table. In the test, the three-way acceleration sensor is used to obtain the cylinder head signal under idling and no-load conditions. 12 kinds of different state waveforms are shown in this figure. In order to verify the transfer learning effect of the proposed method between different devices, the binary fault dataset, the Western Reserve University, was additionally used as the target domain dataset. As shown in this table, a total of 12 groups. In this paper, 3 cases are provided. The first case tests the accuracy of the proposed model. The second case tests the diagnosis ability of the transfer model in different fault domains. The third case tests the diagnosis ability of the transfer model in different device domains. In this one, to simulate the noise pollution of the diesel engine working environment, additive white Gaussian noise is added to the original signal as shown in this formula. The original signal noise and the signal with noise in the normal data are shown in this figure. The diagnostic accuracy of the 3 methods and their different signal-to-noise conditions is shown in this figure. It can be seen that the proposed model had stronger noise immunity, and the lower the signal-to-noise, that is, the greater the noise signal, the more obvious the advantage of CCL. Although the proposed WCCL network can achieve good performance thanks to a large amount of labeled training data, but actually it is very difficult to obtain sufficient labeled data for certain research tasks. As shown in in this figure, and the same noise environment as the label data of the target domain task decreases, and the diagnostic ability is severely reduced. In case 2, split dataset A into two parts to study the transfer effect of different fault domains, named A1 and A2. Assume that A1 represents a dataset that has a large failure rate and is easy to obtain in actual situations, and A2 represents a dataset that has a small failure rate and is difficult to obtain. For purpose of the problem of insufficient samples in the target domain A2, A1 is used as the source domain data for WCCL model training. The result shows that the effect of training A2 based only on WCCL is very poor, and the accuracy continues to decline as the number of the samples decreases. In comparison, the deep transfer learning method A1 transfer to A2 has obvious advantages in accuracy and has less dependence on the number of samples. This case shows that when a certain fault sample is limited, using other fault data of the same device to transfer the learned knowledge to the target task can effectively improve the diagnosis accuracy. In case 3, with diesel engine fault data A as the source domain and bearing fault dataset B as the target domain, the figure shows the result. Similar, the A transfer to B performs better than using only dataset B. This case explains that the knowledge of the diesel engine fault characteristics learned by the proposed model through pro-training can also be transferred to the fault diagnosis task of the bearing. It can be proved that the transfer learning across device domains provides another feasible idea for solving small sample problems. In conclusion, I would like to point out the following aspects. 1. Wide convolution kernel and LSTM can effectively improve the anti-noise performance of diesel engine diagnostic model. 2. As the label data of the target domain task decreases and the diagnostic ability of the deep neural network is greatly reduced. 3. When a certain fault sample is limited, using other fault data of the same device to transfer learned knowledge to the target task can effectively improve the diagnosis accuracy. 4. The knowledge of the diesel engine fault characteristic learned by the proposed model through pre-training can also be transferred to the fault diagnostic task of the bearing. Okay, ladies and gentlemen, that's the brief introduction about my work. I welcome all comments. Thank you.